Okay, good morning. Okay, so I'm going to talk about UV detections of water hydration on the surface of the moon. We've heard about infrared detections earlier today, but here we're going to go to shorter wavelengths. Okay, and we're using LRO Lamp, which is the Lyman Alpha mapping project, in orbit around the moon, and using nadir pointing down to the surface of the moon. It's an FUV spectrograph, so it's covering about 57 to about 200 nanometers. And mainly what we're talking about here is the longer wavelength part of that range, from about 140 or so up to about 190 nanometers. Now, we've heard about some of the LAMP results looking at the PSRs, the permanently shadowed parts of the polar regions, where water ice is detected in a few different studies from Gladstone and Hain, and using LAMP data. Thanks. But what we're focusing on here is lower latitudes. And we are exploiting the strong water absorption feature that appears in the UV. There's a strong water edge at about 165 nanometers shown here. Shortward of 165 or so nanometers, water is very, very dark, and longward of that, it's very bright. And so what we know is that if there's even a very small amount of water, it can be detectable. So it's kind of a sensitive detection technique of very small amounts of water. Thermal emission is not an issue in the UV. What is an issue is signal to noise, because down in the UV, there's not a lot of solar flux, as you may know, to reflect off the surface. And so we need to integrate for long periods of time. We need to look at large regions on the surface to just sum up a lot of photons. So what we initially did was we looked at two regions on the lunar surface, shown in the red and the blue boxes, a mainly highlands region and a mainly mare region. And what we're doing is actually, let me go back. What we're doing is we're measuring the spectral slope. And I don't think I can use a pointer, but we're measuring the spectral slope over about 163 to about 173 nanometers. So right over where that water edge is really strongly absorbing. And so we're saying, well, in our reflected data, in our reflectance data of the moon, any slope changes in there could be due to the presence of water. And we look at those slope changes throughout the day for these two regions. And Brant showed a version of this plot here where we show the variation in spectral slopes throughout the day for our highlands region and our mare region. And we see a distinct change in slope, especially for the highlands region, around the midday. It's stronger in the highlands than in the mare. And what we can do is also plot those slopes versus temperature as measured by diviner. And that's what we've done here for the highlands region. And we can then compare with a model to then try to back out an estimate of the activation energy. And so now what we're going to do is try to push the limits on the data set and try to look at smaller regions on the surface all across the moon. Now, to model the activation energy, we're assuming that what we're seeing is thermal desorption. And so we can model the change in concentration of water with time, shown by this relationship here, which is related to this K term, which includes activation energy, which is U sub E here. In our model, I'll show you that N naught term represents a scalar, which is related to the relative water concentration we are assuming. Now, the activation energy of desorption is the energy required for a water molecule to be released from the surface. And it has been discussed in the literature that the activation energy is related to molecular trapping energy that is a result of defects and impurities in the grains. And so we might expect that rougher, more mature grains might have higher overall activation energies. So here's our map of activation energies. And I don't expect you to see all of these, but I'll just point out a couple of highlights. We are looking at 30-degree longitude by 10-degree latitude bins. So still not very super high resolution, but a lot better than we were doing initially. And we are putting the obtained values, the estimates of activation energy in yellow, and the scalar value in orange. And what we're also doing is that you might see that some of the values are in parentheses, and that's where we're feeling a little bit less certain about the fit. And you can also see that at the lowest latitudes around the equator, we don't do fits. And this is where, since we're looking at time of day variations, this is really kind of closely related also to photometric variations. And so we're very carefully trying to remove photometric variations so that what we're looking at is sincerely time of day and temperature variations. So our photometric correction right now, we're not feeling super solid about the smallest phase angles at the lowest latitudes, so we're not going there yet, and also at the very highest latitudes. Okay, but we do have estimates for activation energy from about 20 to about 70 degrees latitude. Here's some examples of some of our fits. So in the top row is our spectral slope versus local time for a couple of our regions. And then in the next row is the spectral slope versus temperature from Diviner. And then in the bottom row is shown our fits to give you an idea of how well we're doing here. So, I guess I can't. In the lower left, the data are in the blue and the model is in the red. And here we get an activation energy of about 1.3. For the third column over, that is a low latitude, 20 to 30 degrees north latitude region where we don't see a very strong change in spectral slope with time of day. And you can see that the trend versus temperature really doesn't look like thermal desorption is happening at all. So we don't think it's even happening there. So those are just some examples. By the way, the other thing that I want to show you is that on our map, the Mare regions are sometimes harder to fit because there's not a lot of spectral variation happening throughout the day. And the values that we get in the Mare regions are generally significantly different than in the highlands regions. So, and I'll tell you the bottom line here is that the derived activation energies that we get are about 1.07 EV to about 1.4 EV. We're still working on getting error bars on there to distinguish how well we can distinguish, one region to the next. We find that the lower latitudes have higher activation energies. Maybe this is related to space weathering effects that we might expect. Higher latitudes generally tend to have stronger diurnal changes in slope. So a greater change in hydration with temperature, with time of day. And that is also represented by a lower activation energy value in the model. The regions dominated by Mare material do not show a measurable thermal desorption shape, or it's minimal. And so these results, we think, have implications for movement of small amounts of water across the lunar surface. And that's my talk. I'll leave it there. Take any questions.